this problem right here, this is a problem that you've seen before. And I want to work this one in a more physics manner here. Centripetal force. When things are going in circles, something in your brain screams centripetal force at you. And then you ask, okay, so you write down the equation for centripetal force here, right? And then you ask, well, what's the sum of the forces? Remember with the roller coaster, if it was at the top of a vertical loop, it was going to be force of gravity plus normal force, right? If it was at the bottom of the loop, it was going to be normal minus force of gravity, and that sort of thing, right? Well, here you ask, all right, what's the force causing it to go in a circle? Well, it's the force of gravity. So I wrote Fg. Now we have an equation for the force of gravity at long distances. At short distances with the Earth, it's mass times the acceleration of gravity. And g at long distances, it's g m1 m2 over r squared, right? Now, I'm going to work this in pure variable format right now. I'm not going to plug in numbers. I haven't done this in this class just because y'all prefer numbers, but I want to go ahead and start exposing you to that, so whenever you get to college, you're not freaked out by it. I'm looking to get the velocity all by itself. Forget the numbers, who cares? Let's do algebra right now with letters. Heck, they're cleaner anyways. So to get the velocity by itself, the first thing I'm going to want to do is multiply each side by r. You see that? So multiply each side by r. So this, let's grab this entire get up right here, drag it, multiply by r, multiply by r. That way the r's cancel out, yeah? And this r is going to cancel one of those r's. Yes? Okay. So now I'm left with g m1 m2 over r equals mv squared. Next step is to divide both sides by mass. Now, the mass in the centripetal force side is the mass of the thing going around the circle. That's the moon. So let me put m in here. And let's erase my 1s and 2s. Let's get an m of Earth and an m of moon going on there also. Okay, the two masses. So I'm dividing both sides by the mass of moon, right? So that's the same thing as multiplied by 1 over the mass of moon. Yeah? Okay with that idea? Come back. In fact, let's just do this line again. Got a few head shakes. All right, so I've got G, mass of Earth, mass of moon, over R equals mass of moon v squared. Yes? Good question. The things going around in a circle, right? Over here, this has to be the equation, the mv squared over r. That's the centripetal force part of it, right? You always deal that mv squared over r. That m is the mass of the thing going around in the circle. Remember with our centripetal force lab where you had the glass tube and you were spinning it around, the mass you used there in the mv squared over r was the mass of the stopper, thing going around the circle. So the mass in the mv squared over r is always the mass of the thing going around the circle. In this case, it's the moon, right? Trying to get v by itself, divide both sides by mass of the moon. And let me point this out. Dividing by something is the same thing as multiplying by 1 over that. Everybody familiar with this? Yeah? I'm multiplying by the inverse, so maybe I'll do it in that manner. 1 over mass of moon, right? That way the mass of the moon cancels over here times 1 over mass of moon, and masses of moon is going to cancel over there too. Yeah? Leaving me with the velocity is going to equal the square root of g mass of Earth over r. Lots of times physicists love to work it like this just because it's so much cleaner, right? You don't show any of the numbers till the very end. You get this nice clean idea here, and then you plug all your numbers into the calculator, just plug jog at that point in time, right? If you did decide to work this, work problems like this, and you worked it all the way correctly to the end, you get all of your points correct, even if you got the wrong answer, then I take off 1 for a math error. If you did everything else right. Okay. So whenever you did this, what did your velocity come out to be?
1.5 times 10 to the third.
1.5 times 10 to the third. Everybody getting that?
1.7
1.5 times 10 to the third. My smart board's a little off. Meters per second. 1.5 times 10 to the third meters per second. Sounds about right. Right. Okay. Let me take this problem and launch off this into one of your homework problems. Okay. That is identical to this, eerily identical to this, except instead of using gravity, we're going to use electric. Now, I'm not going to do the exact homework problem. Instead, I'm going to set up my own that's pretty much the same. Let's say I've got a proton right here. Okay? Proton, right? And then orbiting around it is an electron. The radius r equals, let's make it 19 picometers for fun of it. Let's make it 19 picometers for fun of it. Go ahead and expose you to this idea of pico. Now, whenever you see a two-letter, whenever you see two letters standing for some unit, right, you don't freak out. The first letter is always the prefix, the second letter is always whatever the base unit is, right? So this is p meters. And you go, what's a p meter? Yes. Kilometers. I've always heard it said picometers. I don't know why. Pronunciation, the English language, who knows? You don't freak out though about this. You simply pull out your reference sheet, right? You find the p, pico. What does pico stand for? -12, right? So that means R here is 19 times 10 to the -12, okay, meters. And that's what we're going to want to use. And then you're asked here, what is the velocity of the electron? What's the velocity of the electron? Something's going in a circle, right? So this screams at you what? Good, centripetal motion, centripetal force. So this is going to be sum of the centripetal forces equals mv squared over r. Right, I'm going to go ahead and put Ne for mass of the electron, because the electron's the thing going in the circle, right? So I'm going to go ahead and put Ne. V squared over r. Now, there was another homework problem where you compared the force of gravity holding the electron to the proton with the static electric force, right, with static electricity, Coulomb's law, holding the electron around, and you found that static electricity was much stronger, gravity. So the force that keeps the electron orbiting the nucleus of the atom is Coulomb's law, right? Proton, positive. Electron, negative. They attract, right? So that's what holds it in. But there's a force acting on this electron that always points inwards, and that's the static electric force, right? Points inwards. That is the centripetal force here. Tyler.
What causes it to have velocity and not just straight into the proton?
All right. Where did the initial velocity come from? Because once it has velocity, right, it's just going to keep going and going and going. As long as it's not losing speed, which we'll get forward to that whenever we do nuclear physics. But
Is it magic?
magic. No, it's not magic. But where did the initial velocity come from?
Magic.
Magic. Sure. Why not? I mean, that's like asking me, where did all the mass of the universe come from? I mean,
Magic.
you have three choices. You have choice A, always been here. Choice B, comes from some outside source. Choice C, magic. Right? I mean, those are your three choices. You know, and magic, it kind of leads down another road there. That's kind of like the end all. You just don't want to think about it anymore. Answer, right? Same thing here. Where did the initial velocity come from for electrons to orbit the nucleus of an atom? You got three options, right? Always been there, always has been doing it. Didn't come from anywhere, not go anywhere, just as is, will always be. Called the static, by the way, model of the universe. Which is kind of weird to kind of disprove it. But anyway, outside force, outside being, or magic, take your pick, don't care what. You choose right now. So, electric force, right, is what holds the electron around the atom. We have an equation here for the electric force. What is it? Good. I have an equation for the electric force, right? I know what the electric force is. K, Q1, Q2 over R squared. Moreover, I now have everything except the velocity. I know what the charge Q1 and Q2 are. Charge of the proton, charge of the electron. Right? Both of those have what charge? What's the charge of a proton or an electron? Yeah, 1.609 or 1.6, sometimes we take it for that. 1.6 times 10 to the negative 19 coulombs. Okay, on your reference sheet, it's listed as the elementary charge. Okay, the elementary charge. And a proton and an electron have to have equal numbers, or has to have an equal charge. They have to balance out. Right? They really want to balance out. So, and do y'all want me to work this through with numbers, or do you want me to work this through with variables?
Variables.
Sure, let's do variables. We'll do variables. K, and this is charge of electron, charge of proton over R squared equals mass of electron, velocity squared over radius. I'm looking for velocity. I'm going to do two steps here at once. Charge of the electron and charge of the proton are the same thing, right? Charge of the electron and charge of the proton are the same thing. One's negative and the other's positive, but I'm going to drop the negative because all negatives mean our direction. That negative is indicating that it's an attraction. I know it's an attraction. I'm dealing with that manually myself at the end. So I'm going to drop that. I get 2 times K Q of the electron over R squared equals M E V squared over R.
Square, yeah,
Oh, thank you. It's not 2 times, it's squared. Thank you.
Why are we squaring K? Because we
Q times Q. I'm not squaring K, I'm squaring the charge. Yes. Yes. Okay.
Just a quick question before you even get there. Whenever you divide like a mass with, and like the radius is gonna be on the bottom, when you just they multiply the depth.
Yes.
Can I need pressure? I'm sorry, I worked it.
No. Times R. Times R. Right? Multiply both sides by R. Radius cancels out over here, and that cancels one of those. Yes? So now I'm left with K Q squared over R equals mass of the electron, velocity squared. And now you can see where I'm going with this, right? I'm going to divide both sides by the mass of the electron, and then square root it. Can I do all that in one fell swoop?
Yeah.
How the rest of it? I'll work it through. So times 1 over M E times 1 over M E. That gives me K Q squared over M E times R equals velocity squared, and then I'm going to take the square root of that entire thing, getting for me here that the velocity equals the square root of K Q squared divided by M, the mass of the electron, times the radius.
What do you do with P2? The same charge, but
Yeah, since, going all the way back up here to this line, the charge of the electron and charge of the proton are the same, right? This is Q times Q. Same charge, 1.6 times 10 to the negative 19, right? So I combine those two into Q squared, okay? If you're doing this with numbers, you would do the algebra the exact same way. Okay, if you're doing this with numbers, you would do the algebra the exact same way. You would multiply, divide, square root. You would do all the same functions in the exact same order, just with the numbers in there. Okay? Technically, I guess if you were doing it all with numbers, you could try to condense numbers all the way down a lot farther, and then just do a quick divide and square root, so to say. Okay? What's the mass of the electron? Someone? 9.11 times 10 to the negative 31st kilograms.
Just on our constant.
It's on your constant sheet. Correct. Constant sheet, all the way at the very bottom, you'll find rest mass of proton, rest mass of electron. Please use it in kilograms right now. Please use it in kilograms. You'll also find rest mass of neutron, but you don't need that right now because neutron has what charge? Zero. And do we care about something with zero charge? We're talking about static electricity? No. Right. Not at all. So what does this velocity come out to be?
9.1 times 20. That's what I got.
What does this velocity come out to be?
Can be good.
It should be big. I'm guessing times 10, somewhere around times 10 to the 6. But that's fine. 8.5 times 10 to the 4th. How about the rest of it?
Wait, what is?
Me too.
Do I need to plug the numbers in? Let's plug the numbers in.
It's the only one I can do.
V equals the square root of K is 8.99, right, times 10 to the 9. So this is 8.99 times 10 to the 9. I can already tell you I need more room.
The actual constant for K is
8.988.
So isn't it 9.89?
Pull out your constant sheet.
8.99.
8.99 according to the constant sheet.
It's 8.988.
The constant sheet will differ a little bit from what I gave you in the notes just due to where we rounded off. Okay? But it should be still 8.9 blah blah times 10 to the 9. All right. Q here is 1.6 times 10 to the negative 19. And just to emphasize what you're doing in your calculator, I would put parentheses around that entire thing there and then square it. Type it in just like I wrote it. Otherwise, what might happen is it might square the negative 19 and then do the 1.6 times 10 to that. Okay, so be careful there. Divided by mass of electron, 9.11 times 10 to the negative 31st, times the radius, which we said was 19 picometers, is that correct? 19 picometers, that's 19 times 10 to the negative 12. And then you square root it. I'd recommend actually practicing punching this in your calculator even if you know other people are doing it because you're going to have to do this at some point in time, in particular on a test, so you might as well go ahead and make sure you can punch it into a calculator correctly and not make some little matters. So what's this velocity from? 6.9 times 10 to the what?
Still the same.
I got 4 points.
Correct answer.
3.6.
That does not make any sense. This does.
I got 10%
A little bit of advice for you. There's the correct answer. By the way, electrons move very fast around the atom. Generally, Now, generally, if it was in a Bohr model, it'd be times 10 to the 6. That's not the order of magnitude that an electron moves around an atom. If you come out with something greater than times 10 to the 8, you got issues right now. The reason for that is the speed of light is 3 times 10 to the 8, and nothing can go faster than the speed of light. As you approach the speed of light, we enter into the realm of general relativity or special relativity, and you don't want to deal with that right now. We'll deal with that in a year. If you go really slow around the atom, well, that doesn't really reflect what's happening here. Be careful with your math. If you struggle punching this in all in one fell swoop, that's okay. I use tons of parentheses. That's how I make sure I get it right. If you struggle punching it all in one fell swoop, that's fine. Instead, don't use letters. Actually plug in the numbers and multiply little step by little step by little step. Okay? I recommend tonight, just going to go ahead and say this, that if we get far enough, I'm going to give you other homework, but I would make this a priority. I would go back to this problem right here and make sure I don't make calculator errors. You got the problem written out and you have the right answer down here. I would try to solve this problem, if I were you, I'd try to solve this problem on my own tonight, try to plug in the numbers and get the right answer. That way I can prove to myself that I can handle all these little / big numbers, whichever it is, because 8.99 times 10 to the 9th is just a number. For some odd reason, whenever students have to plug in something with the times 10 to the 9th or something like that, it freaks them out. You could do it if it was 2 times 3 squared divided by 4 times 5, and then take the square root of that. Everyone in here would get that right. Generally what happens though, whenever it's a longer decimal, and then times 10 to the 9, and all this stuff, something gets punched in wrong or we start to freak out. So go back tonight and practice going through that. I'm here.